In this discussion, let us see some problems on image compression. The compression ratio is denoted by uncompressed file size by compressed file size. It is often written as size suffix u colon suffix size suffix c. For example, an original image has a size of 256 cross 256 single band, that is grayscale image, 8 bits per pixel. This file size will be 65,536 bytes because approximately 64 kilobytes. When we multiply 256 into 256, we get the size as 65,536. After the compression, the image size should be 6554 approximately. The compression ratio is uncompressed size by compressed size, that is 9.999, approximately 10. So this can be written as 10:1, that is 10:1. This is called a 10:1 compression, a 10 times compression, or it can be stated as compressing the image to 1 by 10th its original size. Another way to state the compression is to use the terminology of bits per pixel. For an n cross n image, bits per pixel is equal to number of bits by number of pixels. That is 8 into number of bytes by n cross n. That is the size of the image. We can see another example using the before example what we saw last slide. With the compression ratio 10:1, we want to express this in bits per pixel. This is done by first finding the number of pixels in the image, that is the size is 256 into 256, that is 65,536. We then find the number of bits in the compressed image file, 6554 into 8 bits per byte, that is 52,432 bits. Now we can find the bits per pixel by taking the ratio 52,432 divided by 65,536, that is equal to 0.8 bits per pixel. The reduction in file size is necessary to meet the bandwidth requirements for many transmission systems and for the storage requirements in computer databases. Also, the amount of data required for digital images is enormous. You can see in the next example, to transmit an RGB image, that is color image, 512 cross 512, 24-bit, 8-bit per pixel per color image via modem at 56 kilobaud, that is kilobits per second. It would be take about. So what is the time it will take? So that is the thing we have to find now. So 512 cross 512 pixels into 24 bits per pixel divided by 56 into 1024 bits per second. Here 56 kilobaud is given. This baud rate is given, that has to be multiplied into 1024 bits per second. It is approximately 109. It is approximately 1.8 minutes. This number is based on the actual transmission rate being the maximum, which is typically not the case due to internet traffic, overhead bits and transmission errors. You can see a next example. To transmit a digitized color 35 mm slide scanned at 4000 into 3000 pixels and 24 bits at 56 kilo baud rate would take about the size, that is 4000 into 3000 pixels into the given bits, 24 bits per pixel divided by 56 kilo baud rate is given, that is into 1024 bits per second. This is approximately 5022 seconds, that is 83 minutes, too long to wait. So the example 10.1.5 applies maximum data rate to example 10.1.4. That is, the 10.1.5 says to transmit a digitized color 35 mm slide scanned at 4000 into 3000 pixels and 24 bits at 3 Mbps would take about 4000 into 3000 pixels into 24 bits per pixel divided by 3 into 1024 into 1024 bits per second, that is equal to 91 seconds, approximately 1.5 minutes. Now consider the transmission of video images where we need multiple frames per second. If we consider just 1 second of video data that has been digitized at 640 into 480 pixels per frame and requiring 15 frames per second for interlaced video, then to transmit 1 second of interlaced video that has been digitized at 640 into 480 pixels is calculated as 640 into 480 into 15 frames per second. into 24 bits per pixel. That is divided by 3 into 1024 into 1024 bits per second. It is approximately equal to 35 seconds. Next example is calculation of entropy. Let L is equal to 8, meaning that there are 3 bits per pixel in the original image. Now let's say the number of pixels at each gray level value is equal. They have the same probability. That is P0, P1 till PL is equal to 1 by 8. That is, now we can calculate the entropy as entropy is equal to summation I is equal to 0 to L log base to Pi. That is 1 by 8 log base to 1 by 8 is equal to 3. This tells us that theoretical minimum for lossless coding for this image is 3 bits per second pixel. In other words, there is no code that will provide better results than the one currently used. That is called natural code. For example, 000 2 is equal to 0, 0001 base 2 is equal to 1, 010 is equal to 2. Same way 111 base 2 is equal to 7. This example illustrates that the image with the most random distribution of gray levels, a uniform distribution has the highest entropy. Let equal to 8. Thus we have natural code with 3 bits per pixel in the original image. Now let's say that the entire image has a gray level of 2. That is P0, P2 is equal to L, P0, P1, P3, P4 up to P7 is equal to 0. The entropy is calculated as I is equal to 0 to 7 Pi log base to Pi. So minus of L log base 2, that is equal to added, and this tells us the theoretical minimum for coding this image is 0 bits per second pixel. Why is this? Because the gray level value is known to be 2. To code the entire image, we need only one value. This is called the certain event. It has the probability of 1. We have an image with 2 bits per pixel giving 4 possible gray levels. This image is 10 rows by 10 columns. In step 1, we find the histogram for the image. This is shown in figure 10.2a, where we see the gray level 0 has 20 pixels, gray level 1 has 30 pixels, gray level 2 has 10 pixels, and the gray level 3 has 40 pixels. These are converted into a probabilistics by normalizing to the total number. Next, in step 2, the probabilities are ordered. Now, if we go to the next step, you can understand. So this is the explanation of the previous slide. It is there are 4 gray levels are given. For 0, 1, 2, 3, the number of pixels are shown. 20, 30, 10, 40, etc. So we are calculating the probability by 20 by 100.2, like that we are calculating the gray level value. Next step, we are ordering, that is we have to arrange it in the descending order. Next step, we have to add the last two probability value of the gray level. 0.2 plus 1 is to 0.3. Next step, we have to reorder again. That is, when we add, if the value is higher than the already arranged value, we have to make it to the descending order again. So what we are doing is, again we are arranging it in the way, again adding 0.3 plus 0.3 is 0.6. Now we have to reorder that with the descending order, again 0.6 plus 0.4. We have to shift it. Based on that, we have given the arrow marks. So Huffman coding example, here we are just adding the probability values and then rearranging, adding and rearranging. Then we have to allocate the codes. How the codes are allocated is, the first one will be 0. The least value will be given to the highest probability, that is 0. 1 will be given to the lowest probability, that is 1. Now this 0 from 0.6, how we got this is 0.3 plus 0.3 only we got the value. So moving backward, 0 and 0 is allocated to that same 0.3 and 0.3, and 1 is allocated to the 0.4. In the next step, if we see, we have to add one more 0 and 1 to the right side of the values already assigned. So now it becomes in the, as per the step B, we can see 0, 0, 0, 1 to the point 3 and point 3. Next step 1 is being shifted to point 4 in the second level, that is maintaining the same. Next comes the third step, that is the point 3 is again we got from the addition of point 2 plus point 1. So the 0, 1 will be retained to the point 2 and point 1 as it is 0, 1, 0, 1. And then third bit 0 and 1 is as usual we allocate the lower and the higher part with the probability. Highest probability will be 0 and lowest probability will be 1. So like that we have been allocating the codes in the reverse way, where we start the process from the 0 and 1. Now, since we have only 2 left in our example, we can continue the step 5 where the actual code assignment is made. So like this, the explanation is given for the earlier slide, how we saw how we allocate the codes in the each levels. So when the branch splits, the another assignment of 0 and 1 will occur. Now we have the Huffman code for this image in the next step. So here original gray level, that is code, is given 0, 0, 0, 1, 1, 0, 1, 1. Its corresponding probability is been written 0.2, 0.3, 0.1 and 0.4. So the corresponding Huffman code is 0, 1, 0, 0, 0, 0, 1, 1 and 1. So how to calculate the entropy for this particular example? So we calculate the entropy by adding adding and multiplying the value, that is minus summation I is equal to 0 to 3. This there are three probabilities are given, right? So for the probability 0.2, log base to 0.2, 0.3 plus log base to 0.3, like that we have adding the values. So approximately 1.846 bits per pixel is the final answer. Now length, that is average length, can be calculated by summation I is equal to 0 to L minus 1 LIPI. It has been, after substituting the values of the probability and the length, 1.9 bits per pixel, that is the average length of the Huffman code, is being calculated. So generally in any example, if image size is 256, 256, the image requires 8 bits, that is 2 power 8 is 256. Same way, if an image size is 512 cross 512, it requires 9 bits. 2 power 9 is called 512, right? So the same way we are calculating the number of bits required. Here is then another example of Huffman coding. So here the example is shows the probabilities listed in the descending order A2, A1, A3, A4, A5, and then 0.4, 0.2, 0.2, 0.1, 0.1 are rearranged in a descending order. And this, like the earlier example, as we saw, the minimum probability value of 0.1 and 0.1 is being added. So the 0.2 is being shifted again, rearranged. Again 0.2 plus 0.2 is added in the second stage, that has been rearranged and shifted to the second value, and then 0.2 is brought down. Same way again 0.4 plus 0.2 is being added, again it is brought up, and that is sort and combine has to be performed. Then the codes has been assigned now. So 0 and 1, and the 0 is got for allocated for the 0.6. How the 0.6 is got? From 0.4 and 0.2. So the 0 is being allocated as usual. The 0 and 1 is being written in red color, is being assigned as the right side. Same way for 0.4, we are allocating the 0.2 plus 0.2. It is got from the 0, 0. So then 0 and 1 has to be added to that bits. Same way 0, 0, 1 is being allocated. It coming from the 0.2, 0.1 and 0.2. So 0 and 1 is allocated on the right side. Same way average length is being calculated. So this is another example of the Huffman coding. Thank you.